So let's continue with the linear algebra that we were doing. So this is the second slide set on this topic. So previously we were just doing the basics of vectors, and we introduced matrices, things like that. But now we're going to talk a little bit more about the matrix definitions and things like this. So matrices come in all different types, and it's often useful to categorize certain types of matrices. They have different types of properties, and what we're going to be dealing with are Hermitian matrices, also unitary matrices in quantum mechanics. And so to define those things, we need to first define a few operations. So the transpose, this just means, sorry about this notation, this is not, normally I write the transpose with a little t on the top right. For some reason, the notes that I took this from has slightly different notation, but the transpose, if your original matrix was something like this, then it basically means you flip the matrix along the diagonal. So T12 goes where T21 was, and vice versa. So you can see T21, T12. And so that's just the operation, transpose. But particular matrices have particular symmetries, and the symmetry associated with the transpose is basically these two properties. So a matrix might be symmetric, and that basically means that you take the transpose and it's the same matrix. Basically, that would happen, for example, if these numbers were the same, right? T12, T21. If they're the same number, you interchange them, and of course it's the same matrix. Along the diagonal, it could be anything because the diagonal is unaffected by the transpose. It could also be anti-symmetric. That basically means actually the off-diagonal ones have a minus sign, right? So if this was the negative of this one, so if this was like -3, this would be 3 for an anti-symmetric matrix. But mainly we'll deal with, we'll deal with symmetric matrices also. We'll talk about this shortly, but Hermitian matrices. Now, we can also define complex conjugation of a matrix, and what that basically means is that you just take the complex conjugate of all the numbers here. So all these, you just take the complex conjugate, and you can define real and imaginary matrices, a little bit like how we define symmetric, anti-symmetric. This time the operation is taking the complex conjugate. So a real matrix, T star, is equal to T. And that would of course happen if all these numbers here were real. Yeah. So if all these numbers here were real numbers, then taking the conjugate remains unchanged. The numbers are unchanged, and then you would have the same matrix, and so that would be like a real matrix. If this was a purely imaginary matrix, then you can imagine if all these numbers had an I here, so it's like I, 3i, 5i, like that. Taking the complex conjugate would put a minus sign in front of all the numbers, yeah. And then so that would be a purely imaginary matrix. Okay, so that's what symmetric matrix means. That's what a real matrix means. Now let's kind of combine these sort of two operations, so taking the transpose and taking the complex conjugate. So there's this so-called Hermitian conjugate operation, and what that basically means is taking the transpose and the complex conjugate. So the normal symbol for this is a dagger, dagger, and defined as basically those two operations, taking the conjugate and the transpose. And so, of course, with an arbitrary matrix, what that means is that you've interchanged the rows, these rows and columns, but then all these numbers have got a star in front, so it's just a combined operation of this. And this, you wouldn't really think of this as something that maybe would be very important, but actually it's very important in quantum mechanics. In fact, it's one of the most important things that you need to think about when you're constructing observables, things like that. And we will be dealing mainly with so-called Hermitian matrices. The Hermitian matrix, what that means is that T dagger, that's Hermitian conjugate, is equal to itself. And the reason why this is so important in quantum mechanics is because there's a mathematical property that all eigenvalues of the Hermitian matrix are real. Okay, so if you find the eigenvalues of a Hermitian matrix, we'll do eigenvectors in a minute, but basically all the eigenvalues are real, and these eigenvalues are linked with sort of physical observables. And again, we need some way of, we're starting with some wave functions and things like that, which are complex, but eventually we need to get back to the real world and then have observables which are real, right? So we don't want things like the energy is 5 plus I, or the position is 6 plus 1, 6 plus 3I, or something like this. We only want real observables, and it turns out that any kind of observable is related to some kind of Hermitian matrix. So we'll talk about this in more detail later, but Hermitian matrix thing turns out to be important. This was probably originally, just found as a mathematical fact, but then it later on became very useful in quantum mechanics. So basically, any physical observable becomes this class. Have you guys done this kind of stuff? Hermitian conjugates, transposes, complex conjugates, this kind of stuff? All right. Now, there's a special matrix called the identity matrix. Conceptually, it's very simple. It's just a particular matrix. It's the matrix with all ones in the diagonal and zeros elsewhere, and has a special property that basically it gives back the same vector no matter what vector you give it. So, if you multiply I by any vector, you always give alpha. Now, it's pretty obvious that it does that. But okay, and then so before I say the next thing, so you can also write this matrix also in this form, in the bra and ket form, and you can see that if these are your basis vectors, then all these elements which are along the diagonal. So remember, this was something like the so this would be like the column element. This would be like the row element, right? So basically, if these are the same, then these are all elements along the diagonal. Now, again, it looks pretty obvious. Okay, identity is like this. But there's an interesting, identity matrices have an interesting property that the identity matrix is the identity matrix in any basis, right? So we'll do this in a minute, but here, it's obvious that this just will return the same thing. But actually, you can also work in a different coordinate system and it'll always be the identity matrix. So it's actually quite an interesting property. Okay. So we can manipulate matrices a little bit like how we manipulate vectors, do stuff like we add them, we multiply them. So for example, if you want to add two matrices, then these are distributed like this. So you can add the matrix first, and then perform the operation on the vector after you add the matrices, or you could operate the two matrices on the vector and then add the vectors. You can add the vectors, or you can add the matrices, and get the same result. Now, multiplication kind of works like this. So if you've got, say, two matrices, which are, again, according to last lecture, we can think of the matrices like operators, things that change the state of a vector or change the vector. So, for example, if you had two operators or matrices like T and S, then you could, and remember these matrices, you can think of them like little machines that input a vector and then output some other different vector, right? So if you start with a vector and then you operate on it with T, it'll give some new vector, alpha prime, and alpha prime you can operate on again with S. And you'll get a new vector like this. So you might start with a vector like this, after T it becomes this guy, and then after S becomes this. Now, the way we write that is just as a sequential matrix operation. So, for example, here, this is, the final result after you operate on it with T and then S first. Notice that T comes is on the right-hand side and then S. The reverse order of this thing. So, if you're working like this way, then the matrices, you have to order it kind of the reverse order, if you like, because T is the one that's going to hit A first, and then S will come later. In the matrix language, this means that you're doing a matrix multiplication that looks like this. In general, ST, which is the product of two matrices, not the same as TS. So this is, I don't know why I wrote equals, it's not equals to, in general. ST is generally not equals to TS. It can be sometimes, but in general, no. And so a kind of a measure of how much ST is not equal to TS is so-called commutator. So we write it like this, S comma T. Right? It's supposed to be comma. I don't know, it doesn't look like a comma, but it's supposed to be comma. So brackets S comma T. And that's defined at ST minus T. Okay. So, you can kind of intuitively see that this is like, certainly if ST is equal to TS, then this is going to be 0. And so if it's 0, then you say that these matrices commute. If it's not the 0 matrix, then they don't commute. And the commutator is sort of a measure of how much they are not commutated. Okay, so let's do a little practice. So first one, so this is the Hermitian conjugate. So find x dagger. So what would that be? Yes, same. Yes, because conjugation. First you take complex conjugate, these real numbers, so it's the same. And then you take the transpose, but then this is symmetric, so it's the same. What about y? Take Hermitian conjugate of that. Also the same, yes. Yeah. And z? Also the same. Yes. So actually these x, y, z's, these we're going to encounter them many times as we go through this course. These are like some fundamental matrices that we'll be dealing with for like qubits. Qubits are like the quantum version of a bit. Okay, what about the commutator of x and y? If you haven't done it before, then I think it's a bit hard to do in your head, so feel free to get a pen out, work it out. So let's see, 2I 0 minus 2I. Yeah. Yes. So that's the. I think that's correct. In fact, you could factorize this. Factorize the 2I out to be 1, 0, 0 minus 1. In fact, this thing is z. Yep, that's right. So actually, these matrices, we'll come back to it, have an interesting property that you can work out that they have a kind of a cyclic property like this, x, y, z. So the way that I remember it is that if you try and commute x and y, it becomes, well, z up to a factor of 2i. Right? If you do z and x, you'll get 2iy. Right? And if you do y, z, then you'll get 2i x. If you go the wrong way around, then you get a minus sign. And it's obviously you just get a minus sign because maybe you can press the button, Tongjo. Can you press the bit harder sometimes. The keyboard is. No? Oh. Yeah, just has to press a bit harder. It's obvious that you get a minus sign because, for example, y is xy minus yx. And then so yx is yx minus xy, which is minus of x comma y. So if you there's an ordering to this, so if you go the wrong way around, you'll get an extra minus sign. Okay. Right, and then finally, I think we might not use this very much in the course, but it's still a pretty important concept, so just to still go over it very quickly. So, eigenvalues and eigenvectors. Have you guys seen this before? Yes? Oh, I don't need to tell you really. So, in general, most of the time, when you perform an operation on a vector, it will change the vector, right? So it will, in general, you'll produce a different vector. but particular types of vectors are invariant under the operation. So these are called the eigenvectors, and so if you apply t on an eigenvector, then it'll come back with the same vector up to a proportionality constant. And the proportionality constant is called the eigenvalue. We're not going to do this very much, but actually this is pretty central in general to quantum mechanics, because this kind of tells you the states that are, say, stationary. So, for example, if you remember, if you go back to the first slides when we were looking at those discharge tubes, and then one of the problems was to work out why you only get particular lights coming out of like a neon tube, right? And you only get like this orange kind of light. Well, you get a few other frequencies, but it's mainly orange. And the reason why is because those are the kind of the stable states of the atom, and it all eventually goes back to the fact that these are the eigenvalues of the system, and these are the states. They're stable because basically the operator doesn't do anything to it. So there's a special states that nothing happens to the state, and so they're kind of inherently stable. But anyway, okay, maybe it's too much information. Okay, and then maybe the last thing is this concept of basis transformations. So we were writing these vectors in terms of, some coordinate system. We were saying stuff like, you can decompose this vector in terms of these unit vectors, E1 and E2. But actually, the coordinate system is it's a bit arbitrary. It's a little bit like the same way that, if you've got a coordinate system in space, now I'm looking at it, the ball is, say there's a ball there. The ball is there for me, it's this way for me, but that's only because I'm looking at it. For you guys, you're looking the opposite direction, and so the coordinates of something, like some ball here, will be completely different depending on if I'm looking at it or whether you're looking at it, right? But that's just a freedom of how to choose your coordinate system, and that is basically always arbitrary, really. So there's, a unique kind of physical vector, but the way that you describe it is somewhat arbitrary. There's an arbitrary choice. So I could equally describe the vector in terms of like this red coordinate system, using unit vectors E1, E2. Or I could equally describe in terms of this other coordinate system, green one, E1 dash, E2 dash. Neither is better or worse. They're equally valid. So if you use a different coordinate system, then you will, in general, get different coefficients, right? So obviously, in the green coordinate system, the vector looks kind of a bit different to the red coordinate system. These angles are different. The angle to the green is different to the angle to the red. So these coordinates A1, A2, A1 dash, A2 dash are different, right? Generally. And there's a special operator that makes such transformations, and this is called the unitary operator. And the unitary operator has a special property that Hermitian conjugate is the same as actually the U inverse. It has this particular property. So it's not particularly obvious by looking at this definition of what a unitary operator is, but conceptually the important fact about a unitary operator is that the unitary operator basically performs this kind of basis change. Right? And it needs to be a special type of operator. It can't be any old operator because, for example, it needs to preserve the orthogonality of these things, right? So if you have a rotation, these red vectors just they still have to be 90 degrees after the operation, right? So for example, you couldn't have some operation where, say, took two vectors and then after the operation, say the vectors ended up looking like this. So this would not be a unitary operation. Say, took this vector, turned it into that one, that vector turned, if it doesn't preserve the orthogonality, then it's not a unitary operation. Or for example, if say one of them becomes super long or something like this, this would also not be unitary operation because you really need to preserve one of the properties of unitary operators. Preserves the length of the vector, right? It can't grow or shrink as is implied. So basis transformation is always related to unitary operator, and I'm not really going to go into it, but the definition of unitary operator really is that it has this particular property. I think I think orthogonal matrices are an example of a unitary operator, but not the other way around, as far as I know. Yeah. So it's very similar, yes, to orthogonal matrices, but these can be complex. Yes. Yeah. Okay. All right. So just a little quiz to just get used to this stuff. So, okay, verify that this is an eigenvector of x, and then what's the eigenvalue? So maybe you've done eigenvectors already, then you're familiar with this. But so, what would be the eigenvalue of this one? Sorry, of this this vector for x. Oh yeah, sorry.
For linear algebra, we usually use lambda for eigenvalues.
Oh yeah, well.
Do you still use that, or is there another notation?
Yeah. Yeah. I mean, okay. So probably the way that we. Yeah. So you could write it like that too. So if you wrote t lambda 1 is equal to lambda 1 on the outside and then lambda 1 in the vector, because like a good way to specify, like I said, this is just a name of the vector, right?
Yeah.
So the reason why I got a lambda 1 on the inside is just simply because I'm just calling it that. That's the name of it because that's a convenient name for that vector because that's the eigenvalue of it. So the way that it's often written is something like this, where here's the operator, lambda 1 labels the vector with the eigenvalue lambda 1, and then if I want, I could write this as lambda 1 on the outside, that's just a number, and then here's the vector backing. Right? Now, I wrote it not as lambda 1, but as e, because often in physics, that number actually means something. And for example, it might mean something like energy. Energy, we often use E. E stands for energy. So I think in physics it's less. It's you can do a little bit more what you want. So you don't have to stick to lambda. All right. So in this case, what would the eigenvalue be for this vector for x? Yes, -1. Yes. So just do something like this. So just do the multiplication. -1, 1. This is minus of the original. Actually, all these three matrices, x, y, z, these are called the Pauli matrices. All these have eigenvalues of plus or minus 1. Actually. Oh, I just told you the answer to 2. But you can see, especially for this z, it's obvious because this is already diagonal. And so the diagonal elements are plus or minus 1. But if you diagonalize this one, it will also be plus or minus 1. Okay, then let's do 3 instead. Yeah, okay. So this might require a little bit of pencil paperwork. Rewrite this thing in the basis of that. Might need to give you a hint. But why don't you just first try, see how far you can get. I think you might need some paper or something. Yeah, that's right. Yeah. Okay, so just see how to do it. So the first thing is, so here we've got a relation to take, the primed bases, and then it turns it into the unprimed bases, right? But actually what we want is, to turn this in the primed basis, we kind of need a relation to turn this one. What we want to do is kind of substitute E1 is equal to something primed basis, and then E2 is a primed basis. So the given relation is kind of the wrong way around, right? So the first thing that we need to do is just to invert the relation, and so the way that I do it is to right? Yeah. So normally it's cleanest just to try and add and subtract equations so that I mean, it's tempting just to sort of kind of start to rearrange this, and then you have like E1 is equal to E1 prime minus E2. But then actually sometimes it gets very confusing. And so what I like to do is I always like to keep the primes on one side and then unprimed on the other side, and then never have it kind of mixed together, because otherwise, I don't know. I've got the wrong answer before doing it that way, and so you learn that somehow that there's a right way and a wrong way to do it. Okay, so basically what I usually do is then I just go, okay, I'll add the equations, right? So then I'll get this, and then this one will cancel out because it's got the opposite sign. This one will be E1, and then so basically the inverted relation will be, if I just divide this by root 2, because that's root 2 there, and then this will be E1, okay? And then similarly, E2 is, you're going to get E2 by subtracting 1 from 2, and then so I won't go through it again, but it'll be basically that, right? Okay, so we've done the first step, which is to invert the relation. So we've got now an E1 in terms of the prime bases, E2 in terms of prime bases. And then all we have to do is just to substitute it into the actual state. So this one is E1, so stick it in there. 1. And then this one is plus I. Okay, and then we'll have a half, and then you just collect these terms. 1 minus I. And this is still normalized because actually this 1 plus I, another way to write it is this is E I pi over 4. You don't have to go do this last step, but this makes it more obvious that the state is normalized because we've got the 1 over root 2 here, base vectors, and then these states. Okay. There's the last line. Okay. Any questions on mathematical revision? If not, then let's actually do some quantum mechanics. Okay, so finally start quantum mechanics. All right. So we're going to talk about the wave function. This is basically the central object in quantum mechanics. So, what is the wave function and so forth. So that's what we're going to talk about. So, well, before we talk about the wave function, let's think about what we do in classical physics, right? So, for example, let's take the very typical type of problem that we deal with in high school or first year physics, which is to, okay, here's a ball, and then I'm going to kick it, and then, trying to find the trajectory of the ball at some other time. So a typical problem might involve you being given the initial position of the ball. So the guy kicks the football from this position, and then you might be also given the initial velocity. So it's like the ball initially is traveling at 5 meters per second at this angle, and you've got to find the rest of the evolution after that. Right? And so, the way we solve that in physics is we're given those initial conditions, and then using Newton's laws, whatever equations that you have, you can work out what the position and velocity is some other time later. So this is the general format that classical physics will be dealing with, kind of deals with typical kind of layout of the problem. Right? So it's kind of important to realize what we're actually doing there, which is that essentially, actually this thing is a much more complicated object. It's a ball with actual sort of, dimensions and so forth. But eventually what we first do is we're boiling the system down into kind of the essential variables, right? And then, so, you're so used to solving these problems probably by now that you don't really even think about it. But then, the first guy that had to think about this, you had to sort of think of, what are the important things to take into account here, right? So what you want to figure out how this ball is going to evolve in time, but do we need to take into account of the, the shape of the ball, the mass of the ball, what's important, what's not important, does it matter that it's, brown, all these things, right? Eventually you sort of work out that the essential variables are just position and velocity, and then pretty much everything else you don't have to really worry about. And so what we kind of do is we can sort of say that the state of the ball is this pair of just two numbers. Two numbers basically tells you the crucial information in the system, which is where is the ball and how fast it's going, and then everything else doesn't really matter so much. The fact that it's rotating, all these other things. Eventually, you work out it's not so important. Okay, so I said sort of two numbers. Maybe what I really mean is 4 numbers in this case, because it's say a 2-dimensional problem. So the position is xy position, and the velocity xy velocity. Right? So it's kind of 4 numbers in this case. 2 variables, 4 numbers. Basically tell you the state of the system. Okay, so so classically we are used to doing something like that. So we kind of assign a couple of numbers, a bunch of numbers, 4 numbers in that example, to tell you what the state is. Now, the analogous thing that we do in quantum mechanics is that we describe the system by a vector. Okay. So there's going to be a vector, and that is going to tell you what the state of the system is in. Okay, so basically this is actually the wave function essentially. The wave function is some kind of vector, and that vector is going to be the essential information that everything boils down to in the end. And so you're naturally going to think, okay, so vector, okay, but what kind of vector? Vector in what space? What is this position, momentum? I don't know what space we're in. So I'll get to that in a minute. But basically, this vector will be a somewhat abstract kind of quantity, which is not necessarily something that you can even directly sort of see. And what I mean by that is that, for example, the vector will be a complex vector. So these coefficients, like A0, A1, will be some complex numbers. And that already sort of implies that it's not really something you can directly see. Like it's not really, how do you measure a complex number or something, right? So these coefficients are something that you can't really properly see. I mean, you can eventually measure them, but you sort of have to infer them. It's not like, oh, here's the position, there it is, fine. It's more that these coefficients are there, but they influence the outcome, but you don't necessarily see it. But the actual, these states like 0, 1 to n, so this is the space that this vector is in. So these are actually the distinct states of the physical system. Okay? So these things are actually rather physical. And I'm going to give you a bunch of examples to tell you what kind of things might be these states. But these coefficients can be, well, complex. Okay, so let's talk a little bit about, so what are these states? You know, what space is this vector? What are we talking about? So, for example, these states, so these basis vectors, so there's 0, 1, 1, and you know, these things. So these could be, say, one example, energy levels of an atom. Okay? So an atom has particular energy levels. So people worked that out a long time ago, that you know, the electrons around an atom might be in particular discrete states. Again, this goes back to why neon light only emits orange light. Some discrete levels to the atom. And so that 0, 1, those basis vectors, these might be these energy levels of an atom. Okay? And then, so what does it mean for a state to be a vector in this space of these energy levels? Well, it basically means that the state, it doesn't have to be just in this 0 state, right? So we kind of think like, okay, the atom is always in like state 0 or state 1 or state 2. Actually, it's not true. The state can be kind of like a little bit in 1, a little bit in 2, for example. And that's basically what it means for the state to be, you know, in this vector. Right? So if the wave function, so if these are like energy states of an atom, now these amplitudes sort of tell you more or less like, you know, what fraction is it in state 0 and state 1 and state 2. So a state like this, okay, means you got some coefficients, and then so it's partly in state 0 and partly in state 1. So it's sort of in both at the same time, if you like. And that's an allowed thing in quantum mechanics. We had this example in the introductory slides where we were talking about how an electron might go left and right around a barrier, right? Now, another example of what these states or the basis vectors of the vectors are might be is that, okay, so if it goes left, we can call that state 0. Okay? If it goes right, it's in state 1. So, you know, classically, what we were saying in the introduction is that, well, classically, if you've got some particle, it would only either go left or right. But if it's a wave, quantum mechanical wave, then it might go left and right at the same time. And this is basically what, how you describe such a state in that context. It's, you know, if 0 means left, going left to the channel, 1 means going right. So, you know, if these are like both there, then it's kind of going around both ways of the channel. Another example. So, Schrodinger's cat. So, Schrodinger's cat, say we call state where the cat is alive, we call that state 1. Okay? Maybe if the cat is dead, we call that state 0. Now, the cat can be kind of dead or alive at the same time, if you like. If the cat is in this state, right? So you've got, this is the state that describes the cat. If these are some numbers and they're not both zero, or one of them is not zero, both of them are not zero, then that means that the cat will be dead and alive at the same time. Even more examples. So we can kind of even apply it to sort of the classical case that we were thinking of. So in this case, previously we were saying, okay, the position, velocity of the ball is what determines the state of the system. Now, basically, quantum mechanically, what you could say is that at each position, so there's an infinity of them actually, all of them, different position and velocity, all of them might describe some state. So then it would be like 0, 1, 2, 3, 4, but infinite number of different states here. I've just picked out 2 here, say the state at the top, and then here's the state when it lands. I just call that 0 and 1. Lots of other states actually. And so classically, of course, the ball is either up here or it's down here, right? It's not both at the top and the bottom. It's possible. But quantum mechanically, it is possible. You could have a state, very kind of unlikely and everything, but could have quantum mechanically a state that's both at the top of the trajectory and at the bottom. And that's basically what that state there would mean. It's partially in the top, partially in the bottom. Okay, so I think I've given you a bunch of examples. So I think basically this is always how a wave function kind of looks like. So if we just go back to what we started with, a wave function is always some kind of vector in some space, and that space is basically defined by just individual particular physical configurations or states. And a quantum mechanical state just means that there could be some coefficients that are sitting in front of all these things. So it could be partially in one state or partially in another state. And then it's a complex vector, so that these coefficients are complex. So that's it. That's it for the wave function, really. Now let's look at some sort of limiting cases, if you like. So I've already sort of mentioned this in maybe the ball example, but what we can kind of see here is that really the main difference between quantum physics and classical physics is that basically quantum physics allows superpositions, but classical physics usually doesn't. Right? So, so again, I was saying that the ball was at the top of the trajectory or at the bottom. So this example here. Right? So classically, basically, these are the only 2 states that are allowed. So, in the quantum mechanical language, that would basically mean that my parameters, there's only 2 values of the parameters that are allowed, right? Either A0 is 1 and A1 is 0, or A0, 0 and A1 is 1, right? It's basically, it only allows those 2. Classically, only those 2 allowed. But quantum mechanically, it basically expands on that possibility. So quantum mechanically, you can say, okay, well, let's look at some more states that are potentially available here. So not just these 2, but any 2 numbers here, basically. So in this sense, you can see that actually quantum physics is actually kind of an extension of classical physics. It includes classical physics because by choosing some parameters, you can return back to classical physics, right? But clearly classical physics doesn't contain quantum physics because this is basically impossible in classical physics. So, Venn diagram wise, classical physics is actually a limiting case of quantum physics. One thing which I didn't mention, I said that these numbers could be anything. Actually, they can't quite be anything, and it might be considered a convention of sorts, but the numbers that we take here are usually such that the wave function, or this vector, is normalized. So when we take the norm of this vector, so remember we did that maybe a lecture ago, so when you take the norm of this thing, then it should be equal to 1. And you can see that this implies that these coefficients must add to 1 because maybe you see it already, but if you substitute, so the bra of this thing is n. This, we've got to take a complex conjugate here, n. Okay. That's the bra, and this is the ket. I better use a different symbol here. Okay. And then got two sums here, and I won't write the limits. And these states here, I didn't actually define it there, but I'm going to take them as being orthogonal basis vectors. Okay. So this thing here is going to be Kronecker delta. And then the Kronecker delta will collapse one of the sums, because now m needs to be equal to m. And then we'll have an star, this will be an, and that's an all squared. And we kind of demand that this needs to be 1, so that means that this sum squared should be equal to 1. Okay. And the simplest quantum system that we deal with, and this is very important in the context of quantum computing, is the so-called qubit. Okay? Qubit stands for quantum bit, but it's just about pretty well-known word now. And in this case, basically just the dimension of the system is 2. And what that might mean physically is that maybe you're just looking at an atom and then you're just going to use 2 levels in this atom, or perhaps you're working with some other quantum system, maybe you're working with a photon, then you might be talking about the polarization of the light, horizontal, vertical. This could be kind of anything. Depends on the physical thing that you're looking at. And so qubit general state we write like this. And as we said, the state we normally take to be normalized. And so this basically means that these coefficients, modulo squared, have to add to 1. And a nice way to actually write this is in terms of this parameterization. And it's nice to write it like that because it basically shows you what the actual number of degrees of freedom there are. So firstly, you can see that alpha squared plus beta squared will be equal to, so if you square this one, so cosine squared, and then if you square that one, so this is the same, but so because when you take the modulus, any kind of phase just disappears. So this will be just sine squared over 2. And it's just cosine squared sine squared. It's always equal to 1. Right? So it's a nice parameterization because you can really see that basically in qubit, there's actually only really two free variables, actually. There's theta and then there's phi. Okay? And, naively, you might think that there actually might be even 4 degrees of freedom here, right? These are two complex numbers. So alpha has 2 degrees of freedom, beta has 2 degrees of freedom. Looks like 4 degrees of freedom. But actually, it goes down to from 4 degrees of freedom to 2 because these things have to be normalized. And actually, there's also a global phase, actually. Should I talk about that now? I might just gloss over it here because I think I'll come back to that point later because I don't want to overload you with information. But basically, this global phase thing just means that even if I defined the wave function even if I defined another, so let's say that there's another so I could multiply this whole thing by just another phase here, say xi. In general, because here it looks like I made an assumption that this alpha is a real number, right? But actually, this phase never really comes into the to the measurement of. It never really plays an important role. So often it's just omitted. You can certainly see it here that it doesn't affect the normalization because even if you had that, it would not change the normalization. But actually, it doesn't ever change any physical properties. So even though there's originally 4 degrees of freedom, one disappears due to the normalization. And another one disappears, or it's sort of omitted, actually. It doesn't disappear, it's just omitted because it doesn't really do anything. And so by convention, this factor is just taken to 0. And then eventually you've only got 2 degrees of freedom, theta and phi. Okay. Any questions?
Why is it theta over 2?
Good point, yes. It's for later, basically. A nice way to visualize this state, and maybe I'll just give you a sneak peek. So remember those Pauli matrices that we had before? So X, remember that xy was this, z was this, right? It came up in the question. Now, this is getting a little bit ahead, but if you calculate the quantity like this, where you have the state and then you have the this operator in the middle, what you'll find is that this will be sine theta cos phi. And then this will be sine theta, and then this will be cos theta. Does this look familiar? Okay, so
the sine theta cosine.
oh, whoops, oh, sorry, mistake. Okay, that might make a difference. Yeah. Okay, so this thing is looks just like polar coordinates or spherical coordinates, right? So when you got like coordinates, spherical coordinates, like this. So if you've got something, a vector, and it's pointing and it has a, this is z, this is x, this is y, use different color. So if you've got a vector that's pointing somewhere and it's making an angle of theta degrees with the z-axis, and then let's say like this, and then an angle of phi with the x-axis. Then this is exactly the coordinates that you would get in the spherical coordinates. And so there's an interpretation, it's called the block sphere. You can look it up already. We'll do it later anyway. It's called the block sphere. There's an interpretation of these vectors as, or the states of a qubit, you can interpret as being on the surface of some sphere. Okay? And the reason why you got these theta over 2s is so that eventually you'll get these right angles. If you had just theta here, then this will be like 2 theta, 2 theta, 2 theta, and then the interpretation is a bit ruined. But it's obviously arbitrary what angles you choose here. So that's basically why. We'll come back to that. Okay. All right. I think we'll leave it there then today.